Hello, good morning everybody. This is Dr. Gu again. Welcome back to today's class. So we're going to continue to talk about Flory-Hagen theory. To begin today's class, I want to first recapture what we have discussed in the last lecture about lattice theory. First, what is lattice theory? I'm going to give a qualification test or quiz now, and the question I want everybody to write down and send back to me is related to explain to me what is lattice theory and how does entropy and enthalpy contribute to the lattice theory. And I want everybody to discuss what's your thought about which is favored for mixing, which is not favored for mixing. Okay, you can have about 10 minutes to write this down, and you can send it back to me whenever you have free. Okay, so you can pause now and take the answer for 10 minutes and send to me whenever you finish. Whenever you have finished writing this quiz and answers back to me, you can resume the discussion. So for today's class, we're going to talk about a more related courses to what is our school is Polymer Science and Engineering. So today's lecture will discuss about what is Flory-Hagen theory. So as I explained to everybody, lattice theory actually is doing very well to explain how does solvent mixture, right? So we know that if we mix the toluene and hexane at a different mixing ratio, if we know the Flory-Hagen parameter chi, we can calculate the entropy and enthalpy for each part, and we can know if two materials will mix or not. So this generally is applicable using the lattice series for small molecular, or even in the case of oligomers, but it is not always true for polymer solvent mixture. And one of the major differences is that the polymers, they're connected, so the entropy term, it will be very different compared to any conventional mixture. So in today's class, we're going to first discuss what is actually the Flory-Hagen theory and how does it differs with lattice theories, as well how do we approach it. So here on the screen, we actually had a chance to talk about in the last lecture about what is the Flory-Hagen theory. And we had the opportunity to talk about how does polymer differs with small solvents, right? One of the major differences is that polymers, they are connected, so polymer has much larger volume compared to those solvents. In other words, if you think about if you have one single polymer chain compared to one single solvent molecule, your polymer chain is likely to be much bigger. And as shown in this particular polymer solution model, your polymer chain will behave like these connected black dots, while the solvents will be those white dots without connection. So it's quite obvious. How does this impact the entropy and enthalpy is a question what we're going to do in today's lecture. So we need to define a new term. First is what is volume fraction for a solvents and a polymer. So phi 1 in this case we define as volume fraction for the solvents. And in the solute of the toluene and hexane, because they take the same volume, so we simply have defined a similar term, which is M term, right? But they're different in here. This is for lattice theory, and for the Flory-Hagen theory, it generally is very similar. They only differs a little bit in terms of this V term, V1, V2. And what is V1 and what is V2 is the volume of the solvent and volume of the polymer. So V1 we define as the volume of the solvents. As you can see, that volume of the solvents will be equal to unit volume of the lattice, how much volume each lattice occupy, and M1. M1 is number of lattice you have, right? If you have 100 lattice, then you have solvent's volume of V1 multiplied by each lattice has M1. Well, this one for the polymer is a little bit complicated because not only each polymer not just occupy one volume, it needs to be occupied degree of polymerization and multiplied by V0 volume and multiplied by number of moles of molecular, or just a number of molecular in this particular case. So what this means is that if I have one polymer chain, if M1 and N2 both equals to 1, as you can tell, one solvent occupies just a single V0, and one polymer chain occupies n degree of polymerization multiplied by V0. And if our degree of polymerization is as the length of this black chain, in this case, let's count. So this is a 2, 3, 3, 2. So this is 13. N equals to 13 for the black one. Okay. So now, volume fraction of the solvents will equals to M1 divided by M1 plus M multiplied by M2. Here, M1 is just number of the solvents. M2 is number of the polymer, because the polymer each is big, so that's why you would actually see this N is the degree of polymerization term. Okay, so if you know this, then volume fraction of the phi 2 is a polymer. Quite straightforward, right? So your volume fraction of the polymer will equal to how much volume your polymer have divided by total volume of your system. And volume of your polymer is N multiplied by N2, and total volume of the system is number of solvents plus polymer multiplied by its degree of polymerization. And if you look carefully, it just slightly differs with what we had in previous lecture in lattice theory. This is x1, this is x2, because in the lattice theory they occupy the same volume, and if you assume n equals to 1, you would simplify the Flory-Hagen theory to lattice theory. Okay, quite straightforward, right, everybody? Now, in the Flory-Hagens, the entropy of mixing for a polymer system is more difficulty than simple mixture of two solvents. As you can see, the complexity comes from now a polymer chain is connected, and the connectivity is a major impact on what is our finding here, and I'll explain to more how does connectivity impact our finding. In a simple case, we can also think about the lattice, simple use to the lattice theory, that we just fill the lattice with a polymer chain. But for the solvent, because each dot's either black or white, it's independent, so you can put them wherever you like. There's no restriction. But the polymer is related to connectivity, so where you put them has to be related to where your previous polymer chain components is at. So that's why you start to worry about connectivity, right? And we will be able to discuss a little bit more detail how this connectivity impacts the entropy. In terms of enthalpy, there's not much big differences, and we will discuss as well how does enthalpy differs between lattice theory and Flory-Hagen theory. There is a couple assumption we need to discuss, pretty much similar like we discussed in the lattice theory. Almost every theory needs some assumptions to begin with. So in this particular case, we need to know that first, your conformation degree, or basically how the polymer chain is being behave, will not affect before or after we add solvents. So in other words, degree of freedom in the pure state and in the mixed state are equal. And as we know that in the mixed states, we actually need to consider what is S before mixing and S after mixing. And we can calculate then delta S, which is number of entropy loss during the mixing process. A similar approach we need to use is to get this. S will be equals to Boltzmann constant K ln omega. Okay, omega is number of independent position of molecular can have, or number of configuration, and we will also talk about a lattice size term. If you have number of lattice, it will be L prime, and this defines as total number of lattice. All right, let's take a look. So in the homogeneously mixture of solvent component 1 and 2, each molecular is basically has a freedom of omega 1, 2 equals to L prime. L prime is again number of lattice. But number of the states for each molecular of species 1 before mixing is basically number to how much is being occupied, right? So this L prime multiplied by phi 1 is basically tell you how much number of sides you would have. Now, if you look at here now, we can compute what is delta S and delta S1 and delta S2 for the two different components. How does it depend on different states? And we can simply reach the conclusion that delta S1 will be equals to the volume fraction of phi 1, and delta S2 will be equals to volume fraction of phi 2. And phi 1, phi 2, we already mentioned it's a volume fraction, okay? All right, now let's calculate the delta mix. And this would be equals to number of molecular, each one would have some degree of mixing. So we can use delta S1, delta S2, and M1, N2 is number of polymer chains. And this is one way you can represent, as we talked about in the past lecture. We can either use the K term, Boltzmann constant, or R term as a gas constant to describe this. And this makes the system differ slightly because K term is number of molecule. So if you count the beaker, there's billions of molecules is there, where R is related to moles of this molecule. So this is always going to mole, number of moles. You have 1 mole, that will be equals to 6 times 10 to the power of 23. And N is simply number of moleculars. Okay. Well, then we can reach in the Flory-Hagen theory that your delta S will be related to the volume fraction in the phi 1 and phi 2. In the regular solution theory, it's also the volume fraction of x1, x2. There's no difference, right? The only difference is now that phi terms will be dependent on phi 1 because it's a small molecule and will be equals to 1, and then you would be equals to this term, and phi 2 will be phi 2 m multiply m2 divided by 1 plus n2. This is the same way we have discussed previously, but pay attention to that. There's no prefactor for phi 1. However, for phi 2 there's n multiplied by phi n2 because due to the polymer degree of polymerization, now you have to consider this term. And this makes a huge impact because now delta S, you can either write the for the whole component or divided by normalized by number of lattice. What we mean by normalized by number of lattice is we need to divide what is delta S mix by how many lattice is in the system. And the number of lattice is defined by m or equals to the lattice number, m1 plus n multiplied by n2. This is total available spots you can throw in these white or black dots in that system. Why we want to normalize them? Because since the system is typically considered to be easier to comprehend what happens at each lattice size scale, it's just more simplicity and more easy to comprehend if you consider per lattice. Then you can compare one lattice in one system versus another lattice in another system, right? Then I can totally mix hexane. You know, if you have different moles, the delta S will be different, but if you normalize by number of sites, then you can calculate how does each individual sites differs with each other. And because of this degree of polymerization term is there, it will be reflected as well in here. What you will see is will be inherent to log phi 2 term. And why there is phi 2 divided by n is because if we use this equation, we got delta S mix as shown above divided by n. You will see in the first term we still got minus xk. The first half, this will be m1 divided by n, normalized by number of lattice, right? Log phi 1 plus n2 divided by n log phi 2. And this is directly related to phi 1, but n2 divided by n is not phi 2. And phi 2, as we define, you need multiply by n. So this is basically simplify to n divided multiplied by n. This will be equals to 1, and now you can use this term. And if you consider these, it's basically n1 divided by log phi 2. Okay? And phi 2, right? So that's where this delta mixing per lattice side comes from for Flory-Hagen theory. And keep in mind, this tells you what is contribution for the mixing for each lattice. On the left, it's a contribution from the solvent molecular. It's basically almost the same expression with the lattice side theory. It's number of volume fraction of the solvents multiplied by log of volume fraction. But now, in terms of polymer contribution, it differs. If I write delta S mix for solvents per site, we will reach this delta S mix. Remember, this is lattice theory. And this, let me emphasize, this would be the lattice theory. Okay? This talks about mixing of toluene and hexane. Then you would have, this will be equals to K, x1 log x1 plus x2 log x2. The bracket should be on the left. Okay. What does this mean? This now means if we consider the polymer conductivity, the entropy contribution in the second term coming from polymer into the solvent is very little. If we have n equals to 1,000, a degree polymerization of 1,000 is very common. Think about polystyrene. A 10 kilodalton polystyrene is around 100 dp, right? So totally feasible. But your entropy contribution will be cut by a factor of 100. This means compared to the first term where the solvent entropy, the polymer entropy will be minimal. So all the contribution from the mixing is always promoted by the small molecule. How about enthalpy? Enthalpy actually is not much difference in the regular solution results versus the Flory-Hagen theory. This is pretty much the same, where delta mixing will be equals to number of molecular M1 multiplied by X2 multiplied by chi and multiplied by KT. So please keep looking into this, where you only talk about the two polymers and there's only one chi, right? This chi talks about the penalty that incurs to have one polymer contact with another polymer multiplied by interaction of it contacting itself. In the last lecture we talked about cohesive energy turn. How does this relate to each other, right? In here, the only difference again is going to be replace this phi 2, x2 to the phi 2, and phi 2 is basically volume fraction of second polymer, and you would have m1, number of the first polymer chain, and phi 2, and chi and kt again. All right, so it's pretty much similar. There's no much differences. And if we again consider per lattice site for the Flory-Hagen theory, we just need to divide by number of lattice sites. So this divided by m of what delta H mixed above, and you will see m1 divided by m will be equals to phi 1. So the number of energy per lattice side will be phi 1, phi 2, chi, and kt. And it's very simple equation, as you see, as I show here. This comes down to delta G, which is entropy of mixing, and this comes down to mixing energy in terms of Flory-Huggins theory, and there is total energy of mixing versus mixing per lattice. So total of energy of mixing is showing here, where we shows delta G mix will equal to KT M1, number of solvents, log in phi 1, volume fraction of the solvents, M2, number of polymer chain, log in phi 2, and phi 2 is volume fraction of solvents, volume fraction of the polymer, phi 2, phi 1 is for solvent, and M1, phi 2, chi. And if we consider per lattice sides, we're going to divide the top term by number of lattice number is m, and we would be able to reach per lattice sides. We would have kt phi 1 log in phi 1 plus phi 2 divided by n log in phi 2 and phi 1 phi 2 chi. And this is again the entropy term. It always promotes mixing. Entropy again, no matter if it's divided by number of n or not, this will always be a negative number and will always promote mixing. It's just a -1 or -0.1 difference, but it's always going to be negative. Now the chi is going to be a positive term. Phi 1, phi 2 is always going to be positive. So if chi is positive, you always have some unfavorable interaction to discourage mixing. So it comes down to the battle between the enthalpy contribution and entropy contribution to see which one prevails and dominates the mixing process. And we will talk about in the phase diagram and give everybody some example. This very beautiful theory and very symmetric is very nice. And this simple theory is so powerful that inspired many generations of scientists to look at two problems. First is osmotic pressure, and osmotic pressure we're going to talk about in the next lecture to discuss what is osmotic pressure and how does that impact our impact by the Flory-Huggins theory. Okay. The other more important is a phase diagram. The prediction of the phase diagram can be achieved using the Flory-Huggins theory. Basically, if I have two materials, before I even mix them, I can basically look at the parameters, chi, and volume fraction. I can predict if my new polymer, let's say I made it in my lab, Dr. Gu's awesome polymer with toluene, will they mix or not? I can do some prediction and not necessarily need to go through all the experimental to find their outcomes. Okay. I'll give everybody an example where how does a mixing work. So this is a homework example where we shows if we polystyrene with a molecular weight about 10,000 gram per mole dissolved in cyclohexane at 34.5 degree and at a given volume fraction. Okay, so 10% of solute. That means there's 10% of polymer and 90% of solvents, and we can give everybody one more hint. Is at cyclohexane at this temperature, this will be a Zeta solvent. That means chi will be 0.5. I'll discuss more detail about why 0.5 is Zeta solvent. That will be discussed in a little bit more future. But for now, what you need to know is there phi 2, as I showed everybody, 10% solute. That means volume fraction will be 10%. Phi 1 will be 0.9. That will be the volume fraction of the solvents. Now, we are able to calculate a number of solvents and number of polymer. So we can use the first molecular weight divided by its density to get how much volume polymer would take per mole. So if we know this, we can use this information to back calculate in a certain mixture. Let's say 1 cubic centiliter, 1 ml of the solvent, how much polymer is there and how much solvent is there. Okay, and we can calculate, for example, in 0.9 milliliter solvents divided by what is the number of mole per unit volume, we can get how many solvents is there. We have 0.0083 mole. And multiplied by Avogadro number, which is 6.02, multiplied by 10 to the power of 23, we can reach out how many molecules is there in that 1 ml solvent mixture. And we can do the same for polystyrene. As you would expect, polystyrene will be much less. This will be equal to this number. Now what you can do is apply M1 and 2 values. This will be the M1 value, this will be N2 into the equation. We know M1 will be 5.2 multiplied 10 to the 21. N2, phi 1 would be 0.9. N2 we already calculated here. And phi 2 we know it's 0.1. And we also know chi is 0.5. We can add everything together. Now you can calculate the delta G as free energy for the whole system. And if you apply everything here and get everything right, we would be able to get the mixing of the energy will be equals to minus 1.24 joule. That means delta G is negative. And that's why the polystyrene will be simultaneously mixed with hexane, and as we know, and they should be, because hexane is a Seda solvent, so polystyrene should be able to dissolve there. All right. So this pretty much summarizes the Flory-Hagen theory before we go down to some more content, and I will do a quick summary about what is Flory-Hagen theory. And it's an evolution of the Lattice theory, as everybody see. Lattice theory is a very good beginning. We taught it in the last 2-3 weeks to discuss what the entropy and enthalpy contribution in the mixing. For the Flory-Hagen theory, there's only one minor difference, is when we consider Flory-Hagen theory, the polymer connectivity plays a big role. So when we consider the mixing energy per lattice sides, the polymer contribution is much, much smaller, right? Because of connectivity and dP effect. And delta G is also slightly different with lattice theory, but they are very similar. And using the theory, we also shows how you can predict example how polystyrene will mix or not, and this will give everybody some idea. All right, use the next few minutes I will talk about what is chi parameter. And as we define the chi parameter in the enthalpy part, we define chi would be proportional to interactions between the solvent AB minus AA by itself and half of A and half of BB itself. But in a normal term, because Flory-Hagen theory is so such an abstract term, so how do we interpret in a physical term that everybody can speak and understand, or you can explain to your grandma? That's what I also like to tell my students. You need to know the language so that you can speak non-scientific community. For the polymer community, the Flory-Hagen parameter you can explain as degree of hateness between two species. So when the chi value is high, that means there is high degree of dislike between these two species. They will tend to favor phase separation. They would not favor mixing. And this is also reflected in the Flory-Hagen theory, right? As you can see, when the chi value is high, this will be a positive value, and it will be a large positive if chi goes up. If chi is 1 versus chi equals to 10, if you think about chi 10 means this will be 10 times more positive. That means if it's more positive, delta G will be positive too. That means they're not going to be mixing. Mixing is discouraged. When the chi value is low, that means you would love to mix, and when the chi is as low as possible, that means they were very likely to mix. And I want to also speak about there's values that we need to keep in mind that chi parameter is very much a universal term used to describe interaction between two species, but it's sometimes is oversimplified, right? It's just to say all the binary interaction between two species is encoded in it. But you must be also consider all the details about different molecular level of interaction, such as, for example, if we talk about polyisoprene, then we need to consider what is the chi parameter between what polymer you talk about, what about cis trans content, and what about where the polymer is polymerized. Is that 1,4 position, is 1,2 position, and also about what is temperature. There is one consequence of chi is quite obvious, is where in the Flory-Huggins we know entropy is always favor mixing. But chi parameter is actually if two components will mix. If chi is positive, which is likely most of the case where mixing it will be opposed, where the Flory-Huggins theory tell you a lot of two species may not like to be mixed. And when chi equals to 0, that means it's ideal mixture. There's no energy associated with the interaction. So if we reshuffle pole to a molecular and combine with two molecular, there's just no thermal transition. This is also called athermal process. There's no thermal energy involved. When the chi is negative, it's also possible that chi can be negative. And if chi is negative, whenever you mix and at whatever ratio, you will always promote mixing, because entropy will always be negative. If chi is always negative, then at whatever ratio, whatever content, those two species will mix 100%. They just love to be bonded together all the time, right? So you can simply the adage like dissolves or prefers like. What that mean? If two materials have similar property, they will likely to be miscible. So polystyrene and toluene, they share a large membrane ring. If you look at energy, cohesive energy, they will be very close. So you can use energy, disperse the energy density to predict what is chi. And we will talk about in more detail what this energy is. However, if there's net attractive between species, then chi will be negative. If two species attract, of course. So here is an example where all the chi values are predicted. There's enormous effort has been going into the calculation, measuring, and predicted different chi value between different solvents and polymer. So you can look at what is shown here. I'll give you some example. It will tell you first is what is a polymer is and what solvent is. Oops. Looks like I just crushed my system. So let's go back to our program one more time. All right, we're back. Sometimes maybe the CPU is I used it too much. It's just not able to handle it. Let's slideshow from current. Okay, we are back. So butadiene, for example, if you consider it can be dissolved in toluene, that's the chi value it's actually described, right? So chi value is shown on the far right, and this will be the volume fraction it's being measured. So in this range, the chi will be 0.28. You can see this actually has a negative chi value, where if you dissolve polybutadiene in chloroform, it will always mix. And there's high chi value, that means it is polybutadiene is not so good in the N-hexodexane. All right, so this is actually pretty useful if you want to check if the material will be dissolved or not, and you can refer to this particular table. And additionally, chi is based on this called approximation for counting configuration, because we use this configuration to understand how does two species interact with each other. And there is other assumptions come into play that Flory-Huggins basically said there's not going to be a volume change upon mixing. That's most of the times right, But there's cases there, when two polymers mix, the volume could slightly go down or slightly go up. But in our day-to-day use of Flory-Huggins, you can just assume there's no volume change. That's fine. Okay? And then we didn't talk about free volume. This will be more appropriate in terms of morphology of the polymer. You start to understand what is free volume effect. But I do want to mention about another parameter is basically chi. There is effective. Chi effective basically means what is chi dependence on different temperature. Chi do have a dependence on temperature. Flory-Huggins parameter will increase or decrease with temperature. And that talks about the interaction between two species can be dependent upon how much energy you have inside that different temperature. That means, for example, we show here, you would have a table summarizing what is the Flory-Huggins parameter for different polymer blends. And for example, deuterated polystyrene PMMA, deuterated polystyrene and polystyrene. And you can see A is a constant, B is a parameter that is temperature dependent term as you show here. This is pretty much summarized in here. Chi would be equal to constant and have a dependent inverse temperature dependence shown here. So you can tell A is a constant term, determines where your starting point is, and B term shows how stronger it depends on temperature. For example, deuterated polystyrene PPO has quite stronger dependence on temperature, while PMMA doesn't have much stronger dependence on temperature. If you change temperature, it will be flat, but if it has a stronger dependence, that will show up. Alright, so this pretty much summarized the Flory-Huggins series, and I hope everybody can spend some time to understand what is Flory-Huggins theory and how does this theory can help understand and predict the different polymers' phase behavior. So with that, I'm going to wrap it up, and again, it's quite rare that internet is down, but today I surprised to find that it is the case for the whole Cambridge community where I live. Hopefully it will be back very soon and I can upload these slides. With that, I thank everybody's attention, and I'll see you guys next week.